I'm not sure which particular checks you decided upon, but let me tell you about two checks that I want to do to make sure that I haven't made a mistake here at the board. So I'm going to leave what's in the box and erase some of these other additions. Okay. And the first check I want to make is on Einstein's heart. Okay. We said that Einstein's heart was at a fixed position in the pitcher's frame. Okay, that's the delta x prime equals 0. I want to plug that into these expressions and ask, what comes out? Well, it's going to be simpler than what's in the box. Let's just write it out. Delta x is going to be equal to gamma beta delta t prime, and delta t is going to be equal to gamma delta t prime. Okay, now if I simply divide one of these by the other, what I will get is delta x over delta t equals beta. Doesn't matter what the delta t prime is. So what this tells us is something that, you know, we should sort of be very happy about when we see it. It's that Einstein appears to be moving with the velocity beta in the unprimed frame. Well, that's his kick. That's how we set the problem up to begin with. So the fact that we've gotten back what we put in means that maybe I didn't make a minus sign error or a factor of 2 error. So this tells us that Einstein's velocity in the unprimed frame is beta. Okay, so that's what I call, you know, a sanity check. Now, there's something we can do that's a little bit different than that, but another sort of check. And let's actually imagine that Einstein looks at the pitcher. Now the pitcher sits at a particular point in the ground frame. Okay? The pitcher has, as time goes forward in that frame, no change in position. Delta x is equal to 0. Okay, in that case, let's see what that tells us about delta x prime and delta t prime. Well, if we put in delta x equal to 0 in the first equation, what we can see is that what's in the parentheses has to be equal to 0, which tells us that delta x prime is equal to minus beta delta t prime, or delta x prime over delta t prime is equal to minus beta. Okay, so Einstein is looking at the pitcher. I'm sorry, Einstein, the pitcher, is looking at the catcher, and the catcher is going with velocity minus beta according to Einstein. Well, that makes perfect sense as soon as you say it. You know, Einstein is moving with one velocity and sees, the catcher sees Einstein moving with beta, and Einstein looks at the catcher and sees the catcher moving in the opposite direction, but with the same speed. So this is another sanity check on the sort of linear Lorentz transformation that we've written down. Okay, now I'd like to do something that's a little bit more complicated and involves the idea of whether the Lorentz transformation can ever give us something that Galileo would have been happy about. In other words, does this reduce in some limit to what we all know works in our everyday life when we're moving at velocity small compared to the speed of light. Okay, so what I'd like to do, I'm going to erase the sanity checks, and now we're going to actually talk about, a situation that is real, I would say real physics. And so let's go ahead and ask what happens if beta, the velocity, is very small compared to 1. Remember, I'm taking c equals 1, so beta small compared to 1 means the kick is small compared to the speed of light. So this is a very Galilean or non-relativistic situation. Okay, well, when beta is small compared to the 1, let's look at what gamma looks like. So we know from the problems that when we see something like this with this can also be written as a power of 1 minus a small quantity, that this can be approximately written in the following form. 1 plus 1/2 beta squared. So this is the Taylor series expansion of gamma. And it's very good if beta itself is a small number. Okay, so let's go ahead and use that information to write down the form for delta x and delta t in that limit, that beta is small. All right, so, and I'll write this squiggly in this way to indicate this is an approximation. From the first formula, since gamma is 1 plus a small quantity, we're going to get 1 times what's in parentheses, and then very small other things. So this will be plus things that are, people would say, order beta squared. They're numbers that are very small compared to things that involve beta. So just, to emphasize the point, if we're talking about beta of 10 to the minus 2, then beta squared is 10 to the minus 4. In general, beta squared is much smaller than beta when beta is less than 1. So we're perfectly justified with throwing these things out. That's good approximation. Then for delta t, we can do the same thing. And I will write out this as delta t prime plus, and then I'm going to say other small terms. These are terms that involve beta. Okay, now having done that, I need a little room, and we're coming to the conclusion, so I'm going to erase that. I'm going to divide the top expression by the bottom expression, and I have delta x over delta t on the top, and on the bottom I have delta x prime divided by delta t prime plus this thing divided by delta t prime is beta. So we now have an expression that relates the velocities in the unprimed frame to the velocities in the primed frame, and it includes the effect of the kick in the Galilean limit. So just to draw the analogy to the pitcher's case, this represents the velocity of the baseball that Einstein throws. This is the velocity with which he throws in his frame, and this is the kick. And this is something Galileo would have been very happy with because this is a simple sum of velocities. So in this sense, this Lorentz transformation stuff actually gives us back exactly what we know occurs when velocities are non-relativistic. The question I'd like to ask you is, what happens when we talk about velocities that are a good fraction of the speed of light? Which of these steps can I repeat, and which ones do I have to modify to get the answer to the question?